This is the second part of our unit. This is part B of our lesson on electron configuration. Part A dealt mostly with theory, the basic ideas behind sort of the quantum model of the atom and how electrons act. This lesson is going to deal more precisely with some of the very details of how to figure out where the electrons are in particular atoms. And so in this we're going to talk about three things: electron configuration, orbital box diagrams, and electron dot notation. All of these things are three ways of showing where the electrons are in atoms. And so the first one we're going to talk about is electron configuration. Electron configuration indicates where electrons are in an atom. And so we have our picture of the periodic table that we saw from the last lesson. And so as we said is that as we go across through here, when we go from, say, hydrogen that's right here over to helium right here, that what we're doing is that we're like in the 1s orbital. Then as we go to our next element, which is lithium, lithium's right there. And so in lithium what we've got is that we're in the 2s orbital. And so let's take a look and going on to our next one. That'll sort of give us an idea of what we want to do with this. Now for that, let's talk about, say, hydrogen. Now hydrogen, the way that so hydrogen is our element that's right here, remember? So there's hydrogen. And so for hydrogen, the electron configuration tells you which subshells the electrons are in and how many electrons are in each subshell. So for the hydrogen, hydrogen has one electron. Where is that one electron? It's in the 1s orbital. And so we say 1s for it. It's got how many electrons in the 1s orbital? It has one electron in the 1s orbital. And so we'd say hydrogen would just be 1s1. So that's how that sets up. Helium, though, it has an electron that's in here, and it has an electron that's in here. And so it has two electrons that are in the 1s orbital. So we say 1s, and then since it has two, we say it has two. So it's 1s2. So that would be helium right there. Lithium, though, lithium has one in the 1s, two in the 1s, but then lithium's right here. It has one in the 2s. And so its 1s is filled, so it's 1s2, but then it has one in the 2s, so we put 2s1. Notice that if you add up these superscripts, 2 plus 1 gives us 3, which is the atomic number of lithium and also tells us how many electrons there are in a neutral lithium atom. So that's basically how you set up electron configuration. Continuing on that, if we go a little more complex, then we'd run into one like, say, nitrogen. Nitrogen, if you look on your periodic table, is going to be right, let's see, right here. This is nitrogen right here. Okay, so that's nitrogen, big ol' N, like that. Now, so if we want to figure out the electron configuration, let's look where we have electrons. It has one in the 1s orbital, two in the 1s orbital, so it's going to start off with 1s2. Then it has two more in the 2s orbital, 2s2, and then it has one here, and one here. So it has 3 in the 2p orbital, so we'd say 2p3, like that. So that's how we go about getting what nitrogen is: 1s2, 2s2, 2p3. So sulfur. Sulfur, if we take a look at it, sulfur is going to be located right here. So there's our sulfur right there. And so let's work out what that's going to be. And so it has electrons in the 1s. 1s is filled. 2s is filled. 2p, 3, 4, 5, 6. The 2p6, so we have 1s2, 2s2, 2p6. Then we have to go down to the 3s. We're not there yet. So it has 2 in the 3s, so 3s2. Then it has 1, 2, 3, 4 in the 3p, so it would be 3p4, just like that. And so that would be the electron configuration for sulfur. So onward we go on this, some even more complex ones. Let's look at iron. Iron sits over here is 1, 2, 3, 4, 5, 6 down here, so it would be 1, 2, 3, 4, 5, 6. This should be iron right here. There's iron right there. So let's take a look at what we've got. It fills up the 1s. It fills up the 2s, so 1s2, 2s2. It fills up the 2p, so that's 2p6. Fills up the 3s, 3s2. Fills up the 3p, that's 3p6. Fills up the 4s, It's 4s2. Now remember that we got to the next block is not the 4d, it's the 3d. And it has how many here? It has 1, 2, 3, 4, 5, 6 electrons. So 3d6 is what we get for iron. And so that's how you'd work out that particular electron configuration. So, one even more. Let's try promethium. Promethium sits down here, I believe. Let's see. Promethium, that should be promethium right there. I believe that's promethium. Actually, that's neodymium. I've got a slight mistake on this one. Let's change this instead of promethium. We'll change to neodymium. Neodymium. Alright, so this actually is what neodymium is. And so I'm going to erase that guy down there. He's going to become neodymium now. That's the one we're interested in. Alright, so neodymium right down there. And so to work this out is that, as we said, the 1s is filled. We've got that done. We know the 2s is filled, so 2s2. The 2p filled, 2p6. 3s, 3s2. 3p is filled, so 3p6. The 4s is filled, so 4s2. The 3d is filled, so 3d10, because there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in there, because there are 5 suborbitals. So then we go across. The 4p is filled, so 4p6. The 5s, 5s2. The 4d, so 4d10. The 5p, so 5p6. The 6s is filled, and so that's 6s2. Now after the 6s, if you look at your periodic table, that's when we shift down to that F block, because you sort of see we have cesium, barium, 56, and then we're going to go down to lanthanum that's sort of right next to it, and then to cerium, which is 58. And so that means our next one is going to be this guy right here, then this guy right here, and this guy right here. And so that means we'll have 4f3 because of the fact that there are 3 electrons in that 4f subshell. So this would be what we get for neodymium. So that one's a lot longer. And we could have ones even longer. I mean, we throw up this element right here, and you're going to have one that's really, really long. You got to go through the whole periodic table for it. But this is how you set up electron configuration. Let's work out a couple of problems on this. So what is the electron configuration of the following? So boron's our first one. So taking a look at our periodic table, then we say, well, first thing, where is boron? Well, boron is located right here. There's our boron right there. And so what do we have to do this? We know that we're going to start off with, we have that our 1s is filled, so we'd have 1s2. Then we have our 2s filled, 2s2. And then our 2p would have just 1. So we'd have 1s2, 2s2, 2p1 would be what our answer should be here. And so doing that, we'd say that boron 1s2, 2s2, 2p1, like that. So that would be the electron configuration of boron. As, that's arsenic. If you take a look at arsenic, that's element 33. So going through this, and we won't go back to the periodic table, you can look at your own to do this. So the 1s orbital is filled, so 1s2. The 2s orbital is filled, 2s2. The next one going across is going to be the 2p, and that one is filled, so 2p6. The next one after the 2p is the 3s. That one's filled, so 3s2. The next one across is going to be the 3p, and that one's filled, so 3p6. After the 3p comes the 4s, 4s2, because that one's filled. Then that's the one that's odd, that's the 3d that comes, and we have that one is completely filled, and there are 10 electrons that, so 3d10. And then our last one here is going to be our 4p, and so we have 4p right there, and how many fill up? We go 1, 2, 3 over before we get to arsenic, so 4p3, like that. Alright, now uranium. Where's uranium? Oh boy, uranium's down at the bottom there. It's element number 92. Very, very far bottom, sort of to the left. And so let's see what we can get for this. And so we're going to start off. We know that we have 1s2. That one's filled, and the 2s is filled. Then the 2p6, we've got that. Then the 3s2. Then the 3p6. then 4s2, because we go through the 4s. Then after 4s we have 3d, so 3d10. Then after that we go to the 4p, so 4p6. Then we go to 5s, and that one's filled, so 5s2. And then we're going to get to 4d, so 4d10, then 5p6. And so after 5p6 we go to 6s2, and then after 6s, if you take a look at that, it's actually going to be 4f, so we're going to continue it down here. So we have 4f, and is that one filled? Yes, it is. Count across, and you find since it has 7 suborbitals, has 14 electrons. After 4f, we then would go to 5d, and 5d fits 10. And then after that, we go to 6p, which has 6. That end of that 6p is going to take us all the way to radon. And then after that, we go to 7s. So we fill that one up, the 7s2, that takes us through radium. Now we're on to the 5f, and that's the one at the very bottom, and uranium is the third one over, so we'd say 5f3. So this is uranium. This is sort of, it's really long to write this whole thing out, but that's how you'd write out the electron configuration for uranium. All right. Next topic here is going to be on orbital box diagrams. And an orbital box diagram is very similar to an electron configuration, but it shows both what orbitals the electrons are in, and also the suborbitals. Remember that we talked a little bit about suborbitals in the last section, and we said that in a suborbital you could fit an electron that has spin up or an electron which has spin down. And so basically, as we go through that, is that this shows that you have the spin up and the spin down of each electron. And so if we wanted to draw out the electron configuration for hydrogen, the first thing you're going to do is that when you're doing this is that you're going to write out the subshell. So 1s would be our first one, and you do a box under it because the s orbital has how many suborbitals? It has 1, so we do 1 box. 2s, when we do that, we'll have 1 box because it's an s orbital. But when we get to 2p though, the p orbital has 3 suborbitals, so we do 3 boxes like that. And so that's how you'd set it up. Once you go to put electrons in it, the first electron can be an up or down spin electron. It doesn't matter. So for hydrogen here, you can sort of see that what we've got for this orbital box diagram, we've labeled what the subshell is. We have the 1s there. We have 1 electron in hydrogen. It could be up, it could be down. I like putting up first. That's just my own personal preference. And so that's how that sets up there. For helium, helium has 2 electrons in the 1s. Since it's 2 electrons, there'll be 2 arrows. But since that the arrows have to be different, you can't fit 2 ups or 2 down, 2 spin up or 2 spin down electrons in the same suborbital. One of them has to be up, the other one has to be down, and so that's how you set that up. Remember that you have to have each suborbital or each subshell filled before you go to the next subshell. So we couldn't put we couldn't say, oh, well, there's a 2s right there, we'll put 1 right there and not include 1 there. That's incorrect. That's like wrong, because you have to fill up each subshell before you go on to the next one. So our next one will be lithium, has 3 electrons. 2 of those are going to go in the 1s, so it has an up and a down. Then it has 1 in the 2s, so that's like that. Oxygen, let's look forward to that one. And so we've gone through is that it fills the 1s, that's taken care of. It fills the 2s, that's taken care of. Now we get to the 2p, which has 3 suborbitals, and so it has 3 boxes. Now, oxygen has how many electrons in the 2p orbital, or a 2p subshell? It has 1, 2, 3, 4. If you count off, it has 4. So we have 4 arrows here. Now, this configuration that it is right here, where we have 2 in the first and then 1 each in the second and third, this is necessary. The reason why is something that is called the Aufbau principle, German word. Basically what it means is that electrons are all negative. They don't want to be near each other. And so they're going to try to spread out as much as possible. So if I have 1 electron that's in the 2p subshell, then it can go anywhere it wants to. It can go to any of the 3. You could think of it like hotel room beds. And suppose that you have a hotel room that has 3 beds, and you have 1 guy who's staying in this hotel room. Which bed does he sleep in? Whichever bed he wants to. So he goes in the first one. So if we had one electron here, he's just going to be one up arrow right there. Now, we had a second electron. So this would be like carbon for the 2p. Now, that second electron, he comes to the room. He comes in and he sees there's one guy in the first bed and two empty beds. Where is he going to sleep? Well, let's think about this. This is a guy. Do guys like to sleep together when they go to hotel rooms? Generally not. They're going to try to take separate beds if they can. And so he's not going to sleep in the first bed. He could sleep in the second or the third, but he won't be in the first. He absolutely won't be in the first. When we get to the third electron, then he's got really no choice. He will not sleep in the beds with the first two guys. He will sleep in the one with the third one there. And so the electrons, because they repel, always want to get as far away from each other as possible. And so they will spread out to all three suborbitals first before they start doubling up. Now back to our hotel room. We have three beds, three guys in each of the beds. A fourth guy comes in. Where is he going to have to sleep? And we're going to assume he can't sleep on the floor or in the bathtub or something like that. You guys who are listening probably would think some of you would want to do that. But he has to sleep in a bed, so he has to share one, and so he'll be a down arrow that'll be down like that. And so that's what we have here for the oxygen. Is the oxygen has 4 electrons. Is that it's put one in each of the 3 suborbitals, but then it has a fourth one, so it has to go in the other one. It can't be an up arrow, it can't be a spin up electron, because then it wouldn't fit. So it has to be a spin down, and so that fills like that. And that's how you'd set this up for an orbital box diagram. Continuing this, let's try drawing some out for, say, phosphorus would be our first one. Now phosphorus, in taking a look at this, is it has some electrons that are in the 1s. And so we start off with the 1s, so we have our box right there. The 1s is filled, so it has an up arrow and a down arrow, so that one's filled. Once that one's filled, it goes to the 2s. Phosphorus does have the 2s filled, so it has an up arrow and a down arrow. 2s only has one. The next one after 2s we go to is the 2p. So we do 3 boxes because the p suborbital, or the p orbital, has 3 suborbitals. And the 2p is filled. So we are good on that, and so we say one here, one here, one here, and now it's going to put ones down here, here, and there. So that gets us to the 2p, and that looks like an F, but that's a P. So that gets us to the 2p. After 2p is 3s. So there's our 3s orbital. We have an up and a down. Then we're going to go into the 3p. That has 3 suborbitals, so we've got it like that, and so this will be an up and an up and an up like that, and so that would be the orbital box diagram for phosphorus. Now I do want to note one thing, and that is, if you have an unfilled box, you have to draw the unfilled box there. Like if we had ended this at the second, if we were doing, instead of phosphorus, doing silicon, you would have an empty box. You have to draw the empty box, because if you don't draw an empty box, you're basically saying the p orbital, that p subshell, only has 2 suborbitals, and it doesn't. It has 3. Even if one is unfilled, it's still there. So that's phosphorus. Our next one here would be chromium. Chromium's a little bit larger. If you look at chromium down there, it is sitting as element 24. And so let's draw out chromium. The first one would be the 1s, and that one's filled. Then we go to the 2s, and then that one's filled. Then we go to the 2p, so that has 3 suborbitals. So 2p right there. That one has 1, 2, 3, 4, 5, 6. So that one's filled up. After that, we go to our next one, which is the 3s. 3s is filled, so an up and a down arrow there. After that comes the 3p. It's a p orbital, so 3 subshells. An up, an up, an up, a down, a down, a down. We still haven't got the right number of electrons for this yet. And so after that we go to the 4s. So 4s only has 1 suborbital, but it is filled. Now we go to our next one, which is going to be the 3d. D orbitals have 5 suborbitals. So we draw out all 5 suborbitals like this. We write over it. This is the 3d on that. And we first say chromium has how many electrons that are in that d orbital. We count over 1, 2, 3, 4. So it's going to go 1, 2, 3, 4. And so that's how you draw it there. because the fact we have one box over there which does not have one suborbital doesn't have an electron in it, so we just leave it blank. No doubling up because they're all not filled yet. So this would be chromium here. Our next one here is argon. Argon is element 18 if you look over there. And so we'll start this up again. So we have one s like this. The 1s orbital is filled. The next one is going to be our 2s orbital. And you do have to make sure you label each of these. You have to make sure you say whether it's 1s or 2s or 3p or whatever like that. So 2p is our next one, and that one is filled. So we have our up arrows, we have our down arrows like this, so that fills the 2p. Then after that we have our next suborbital, which is in the 3s orbital. That one is filled. Then we go to the 3p. So we have 3 suborbitals in a p orbital, so 3p. So argon here is all the way, it has 1, 2, 3, 4, 5, 6 electrons in that 3p. So 1, 2, 3, 4, 5, 6. It is a completely filled shell, and so this right here would be what we get for our argon. So we've got that. These are basically how you do orbital box diagrams. And so one other topic to talk about before we finish up this lesson, and that is going to be on electron dot diagrams. So first topic here is valence electrons. Key word here is the word valence. There is a same word pronounced differently called valence that you may have heard of with respect to curtains. Valence curtains are curtains that are at the top of the windows, and so not ones hanging all the way down, but the ones just sort of go right across the top of the window. And the reason why they're called that is that word valence or valence basically means top. And so the valence electrons are the ones that are in the highest energy level. They're the ones on the outside of the atom at the very top. And so basically whenever you see valence like that, you basically should think top, right, like that. So these are the top electrons, the ones that are on the very highest energy level. And so if we take a look at something like, say, hydrogen. Hydrogen has an electron on the 1s orbital. And so its highest energy level it has electrons in is the first energy level. So how many electrons in the first energy level? Just one. It has one valence electron. On the other hand, carbon has 1s1, then 2s2, then 2p2. And so its highest energy level is the second energy level. And so as a result, it has 1, 2 from the 2s, and then 1, 2 from the 2p, a total of 4 valence electrons. And so that's how many it has. Now, if you look at something like iron, iron's number 26, it has its highest energy level is going to be the fourth energy level because it has those 4 s's for what's potassium and calcium. So it has a 4s2 and then a 3d6 after that. So its highest energy level is the fourth energy level. It has 2 electrons there. It then has 6 that are in the 3d. Since they're in the 3d, third is not the highest energy level. It has the fourth. Iron's only going to have 2 valence electrons. So you have to sort of look and make sure that you're only using the ones in the highest energy level, but that's how you do it. So, for electron dot diagrams. Electron dot diagrams is a way of showing where the valence electrons are, and on those, the first step you have to do is figure out how many valence electrons you have. So our first example here is hydrogen. We said it has 1 valence electron, and we know it has 1 valence electron because of the fact that it has 1 electron in the 1s energy level. Its highest energy level is the first. It only has 1 electron there, so it has 1. So in order to do this, what you'll do is to show that it has 1 valence electron, you will write out the symbol H, and then you're going to put 1 dot next to it. And that 1 dot is going to tell you that this has 1 valence electron. Our next one is number 2 here is nitrogen. And so for nitrogen, we take a look at that, and we can see it's element 7. Its highest energy level is the second energy level, and it has 2 in the 2s and 3 in the 2p for a total of 5 valence electrons. So it has 5 valence electrons. So it's going to have 5 dots around it for the electron dot diagram. The rule that we want to follow is that we only there are basically 4 sides. So if we have sort of element X here, is that you can put dots on the top side, you can put dots on the side, you can put dots on the bottom, and you can put dots here, but you only put 2 each. So I can put one here, 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 and that's the most. Those are the places they can go. So for our nitrogen, which has 5, it'll have one on top, one on the side, one on the bottom, one on this side, but now it's only 4. It needs a 5th one, so we'll double up on one of the 2 sides. So that would be how you draw out the electron dot diagram for nitrogen. Our next one would be boron. Boron, taking a look at this, is element number 5. It is the first. It has 1 electron in the 2p, so its highest energy level is a second energy level, and so it would have 1, 2, 3 valence electrons. And since it has 3 valence electrons, well, it'll have 3 dots. The only rule is they can't be on the same side as each other, because like the guys in the beds, the hotel rooms, is that they're going to try to go to a different side if they can. They're never going to fill up one bed before the others have someone in them. Our last one here is neon. Neon, if you take a look, that's element 10 sitting over there. And so from element 10, that one's highest energy level is still the second energy level. And how many electrons does it have? It has 2 in the 2s, 6 in the 2p, for a total of 8. And so it has 1 here, 2, 3, 4, then it has 5 doubling up there, 6, 7, and 8, like that. And so that's how you draw out the electron dot diagram for neon. And so since it has 8 valence electrons, note that it's not possible to have more than 8 valence electrons. That's simply the most that you could possibly do. And so that finishes up this lesson. So we'll get on to something new next time.